In the Bohr model of the hydrogen atom, electrons move about circular orbits that are fixed distances from the center of the atom. This is a great model and it seems to work well and explains the emission spectrum of hydrogen. However, no one really knew why the orbits of the electrons were limited to certain distances from the nucleus. So there was more work to be done in developing the quantum theory. Louis de Broglie made the first steps towards the modern quantum theory. He proposed that if light has both wave and particle properties, then perhaps matter has both wave and particle properties. He recognized fairly quickly that if electrons behaved as waves, this would account for the fixed energy levels proposed by Bohr. The reason being, if an electron had wave-like properties, then it would be restricted to orbitals that had radii corresponding to whole numbers of wavelengths. And I'll show you what that looks like in the next slide. So imagine a circle, but rather than thinking about a particle that is moving around that circle, think about that circle as being a wave. Now, in order to form a closed circle, then that circle must be composed of a whole number of wavelengths. If that is the case, then the circumference of our circle must be equal to an integer number of wavelengths. Now, this is important because if our circle is not an integer number of waves, then what happens is that we end up with a circle that doesn't close, and as we go around again, we'll start getting destructive interference. So it just won't kind of work, right? The circle would be unstable, it would interfere with itself, and the particle would be destroyed. So if the electron is a wave, then it has to occupy, and it's also moving about in a circle in space, then those circles must be whole numbers of wavelengths in order for the electron to be stable. So de Broglie has found an explanation for why only certain energy levels can be allowed. So what de Broglie did was he combined Einstein's equation for mass-energy equivalence, you probably know this, E equals mc squared, with the equation for the energy of a photon. So if you replace C in these equations with the velocity of the electron, you end up with the de Broglie equation for the wavelength of any particle. And there it is there. Wavelength is equal to Planck's constant divided by the mass of the particle multiplied by its velocity. So for any particle, we can calculate its wavelength. So let's do an example. It says, what is the de Broglie wavelength of a 142 gram baseball thrown at 44 meters per second? Now, it's important to realize when you're solving for the de Broglie wavelength that you must express the mass in kilograms. This is a result of the way that the joule is defined, and the joule is defined as 1 kilogram per meter, or meter squared per second squared. So let's go ahead and write our formula out. Wavelength is equal to Planck's constant divided by mass over volume. So Planck's constant, 6.626 by 10 to the negative 34. And rather than writing joules seconds, I'm going to use these units for joules, and I'm going to write it out with the full kind of base units, if you will. So Planck's constant in the base units of the SI system has those units, and that kind of reminds us that our mass needs to be in kilograms, so 0.142 kilograms there, and then our velocity is 44 meters per second. So the per seconds go, the kilograms goes, and one of our meters goes, and that makes sense that our wavelength, because it's a length, would have units of meters. So let's put all of that into the calculator and see what the wavelength of a baseball is. And so the wavelength of our baseball to two significant figures is 1.1 by 10 to the minus 34 meters. And so you can see a baseball, an ordinary object moving at typical speeds, has a very small wavelength. That is, the wavelength is smaller than the size of the object itself. And so that's why we don't normally observe the wavelength of things like baseballs. So for most ordinary particles moving at ordinary speeds, we find that the de Broglie wavelength is very, very small, much smaller than the object itself, and so it is unobservable. However, when we have particles like subatomic particles, maybe moving at very high speeds with very small masses, so things like electrons, protons, neutrons, atoms, etc., what we're going to find is that the wavelengths are long enough that they become very important. So what we're going to see is, just like light, matter is sometimes best explained as a wave, and sometimes it's better to explain matter as being a particle when we're doing calculations concerning its properties and behavior. So it's an interesting phenomenon that we have here. We call this wave-particle duality. So let's look at the wavelength of a much smaller particle. So it says, what is the de Broglie wavelength of an electron? And then we're given the mass of the electron in kilograms, moving at 99% the speed of light. So the wavelength is equal to Planck's constant divided by the product of the mass and the velocity. So 6.626 times 10 to the minus 34 kilograms meters squared seconds to the minus 1, that's the units of Planck's constant in terms of the SI base units, divided by the mass, 9.11 by 10 to the minus 31 kilograms, times by the speed, which is 99% of the speed of light, and there it is. So again, kilograms cancels, seconds to the minus 1 cancels, and 1 of the meters cancels. So this will give us the wavelength in meters. So let's put this into the calculator. And we end up with two significant figures, 2.4 by 10 to the minus 12 meters. Now that seems very small, but we want to keep in mind that the diameter of an atom is about 10 to the minus 10 meters. So what this means is that this is about 2.5% the diameter of an atom. So that's a kind of significant wavelength. And it turns out that if we don't consider the wavelengths of electrons, then we can't accurately predict their properties. So people realized quite quickly that we're going to have to think about how we talk about very small particles like electrons in atoms. So normally when we're thinking about a particle of matter, we consider them to have a distinct location and to be moving at a precise measurable speed. But waves are more diffuse. Waves are spread out across a region in space, aren't they? If we think about a wave, where is the wave? Well, it's everywhere the wave is. So if matter has both wave and particle properties, it turns out that there is a limit to the degree of certainty with which you can know its position and speed. And a guy called Heisenberg figured out what the limits are in determining the position of and speed of a particle. And this is described by what we call the Heisenberg uncertainty principle. So the Heisenberg uncertainty principle states that the product of the uncertainty in the position the mass and the uncertainty in the velocity is always greater than or equal to Planck's constant on 4 pi. So what this means in practicality is that the more accurately you know the position, the less accurately you know the velocity, and vice versa. The more accurately you know the velocity, the less certain you can be about the position. So that's it. There's a limit in how well you can both know these things, and you can never know both of them perfectly. If you know one of them perfectly, you know nothing about the other one. So there's a little joke about this, and it says Heisenberg is driving down the freeway and he gets stopped by the police. The policeman comes to the window. Heisenberg winds the window down, and the policeman asks him, "Excuse me, sir, do you know how fast you are traveling?" And Heisenberg says, "I don't have a clue, but I know exactly where I am." And that illustrates this principle. So generally, these are just sort of a solve for the unknown type problem. So it says here, what is the uncertainty in the position of an electron? So we're trying to figure out what delta X is. And so this electron has a mass, or just like all electrons, of 9.11 by 10 to the minus 31 kilograms, and it's moving at 95 plus or minus 2% of the speed of light. So the uncertainty in the velocity is 2% of the speed of light. Okay. We do know the mass, of course, 9.11 by 10 to the minus 31 kilograms. So let's begin this by writing out the Heisenberg's uncertainty principle. Delta X times by m delta V is always greater than or equal to h on 4 pi. So we're just going to solve for delta X by division. As every term here is positive, we won't be flipping the sign of the inequality. So the uncertainty in the position is greater than or equal to Planck's constant divided by the product of 4 pi m delta V. So let's see what we got here. Delta X is greater than 6.626 by 10 to the minus 34 over 4 times pi times 9.11 by 10 to the minus 31 times 2% of the speed of light. So let's see what we get. 6.626 by 10 to the minus 34 divided by 4 times pi times the mass times 2% of the speed of light. And so the uncertainty in the position is, to 3 significant figures, this many meters. So it's not much, but you can perhaps see that that is close to 10% of the diameter of an atom. So it's a significant uncertainty, right? It's important for what we are looking at. Okay, so these are the first major steps in the development of the new quantum theory. So we have 2 key results. We can now calculate the de Broglie wavelength of any particle, provided we know its mass and velocity. And as particles have wave-like properties, then their velocity and position can only be known with a certain degree of certainty, and the amount of uncertainty that we can that are in these measurements is given by the Heisenberg uncertainty principle. So the next major step in the development of quantum mechanics was carried out by a guy called Erwin Schrödinger. And so he brought together these two ideas of matter waves and the uncertainty principle to develop what is now known as the Schrödinger equation. So Schrödinger's model is a model based on probability. And sometimes it kind of generates results that are not the easiest to interpret. So to kind of explain some of these, what seem like paradoxes, Schrödinger described a thought experiment called Schrödinger's cat. So we'll go through that thought experiment now. So in the Schrödinger's cat thought experiment, you have a box that is divided into two sections by a barrier that allows gases to move across it. In one of the sections, you put a cat, and the cat is very much alive when you begin the experiment. In the other half of the experiment, you have a pretty elaborate setup. You have a Geiger counter that, if it is triggered, causes a hammer to fall, and that hammer breaks a vial that contains a toxic gas, and that gas will kill the cat. So to trigger the Geiger counter, you have a piece of radioactive material in there, which it produces a radioactive particle randomly, but on average every 1 hour. So what you do is you assemble all of this and you put a lid on the box so you can't see inside, and you wait for 30 minutes. So then you're asked to describe the status of the cat using statistics without opening the box. And, well, what can you say? Well, the cat's been in there for half an hour, so it has a 50% chance of dying, and also has simultaneously a 50% chance of being alive. So therefore, the best way of describing the cat is that it is half dead and half alive. Now, of course, there's no such thing as a half dead or half alive cat, but statistically, that's the best that we can do. So when we're thinking about small things like electrons in atoms, we can't observe them in any way, and any attempt to observe them only causes them to move. So we have to use statistics to describe where electrons in atoms are, and those statistical models are not necessarily going to make a lot of logical sense. There's no guarantee that they're going to be easy to interpret. So we need to be a little bit mindful of that. So Schrödinger's equation allows us to calculate the energy of a particle in an atom. Well, in fact, it allows you to calculate the energy of any particle, but it can allow us to calculate the energy of an atom, and in particular, the energy of the electrons in the atom. Now, this is the equation. It's the Hamiltonian operator acts upon the wave function to give the energy of the atom for when it has electrons in that wave function. Now, we don't need to know anything about Schrödinger's equation other than a couple of key points. The wave function is a mathematical description of the electron's matter wave, and to calculate the wave function, we need 4 quantum numbers. We have to put 4 different numbers in that define the wave function of the electron: N, L, ML, and MS. Now, if you can compare this to the Bohr model of the atom, to calculate the energy of the electron, we only had to put in 1 quantum number, which was N. So the Schrödinger equation is definitely more complicated. So in chemistry, we generally don't talk about the wave function of an electron. In an atom, we'll tend to talk about its orbital. So it's important to recognize that orbitals are not the same as the orbit of the Bohr model of the atom. An orbit is a circular path that an electron would travel about the nucleus of the atom. The orbital is a mathematical description of an electron's matter wave, and it's not necessarily going to be describing a circular path. The wave function is interesting because if you square it, you get what's called the probability density of the electron about the nucleus. That is, squaring the wave function tells you where the electron is located with respect to the nucleus. For this reason, a very common way of visualizing the wave function is as what we call the radial probability distribution. So what we will have is the radius, the distance from the nucleus, plotted against the probability of finding the electron, and it'll tend to be like a hump shaped curve, and that's telling you the most probable distance that the electron will be from the nucleus. So this little graph that I've been drawing on is the radial probability distribution function for the ground state of the hydrogen atom. It's basically giving you the number of electrons at a given distance from the nucleus. So it's kind of interesting, right? According to the Bohr model, the electron is always at a particular distance from the nucleus when it's in the n equals 1 level. But according to the Schrödinger model, it spends most of its time at the distance predicted by Bohr, but sometimes it's a lot further away from the nucleus than that distance, and sometimes it's a lot closer to the nucleus than that distance. So it's got that little bit of fuzziness in there because the electron is really a wave, not a particle, and there is some uncertainty associated with its position. But the Schrödinger equation predicts that the electron in a hydrogen atom will most likely be found on the surface of a sphere, and it's at about the same distance as what the Bohr model predicts for the n equals 1, n equals 2, n equals 3 level, etc. So it does everything that the Bohr model does, but a little bit extra, right? It includes that fuzziness because the electron is better described as being a wave when the electron is moving around the nucleus of the hydrogen atom. So that all of the curves that we've seen so far have been for the n equals 1 level. And now we're going to look at the curves for the n equals 2 and the n equals 3 level of the hydrogen atom. And you can see it kind of gets interesting. The solid line is n equals 2, and there's some interesting features here. There are and these features are like this. First of all, there's a point where the probability of finding the electron drops to 0. So there's one point there, we call that a node, where the probability of finding the electron drops to 0. But what's interesting is if you go even closer to the nucleus, the probability of finding the electron then rises. So that's kind of cool. This is the most likely place to find the most likely distance to find the electron in the n equals 2 level of the hydrogen atom. When we go to n equals 3, we see some interesting features. We get 2 nodes now, and then we get a couple of humps that are way in close. And then here we have the most probable distance, which is further out than found in the n equals 2 level. So that's kind of interesting, right? Okay, we get that general trend of as we move to higher n values, the electron is found further away from the nucleus, but there's quite a lot of complexity in these curves. They have nodes, and then they also have these peaks where the electron, what they call, penetrates quite close to the nucleus. So the position of the atomic orbital is described by 3 quantum numbers. We'll find out that there is a 4th quantum number that goes into the Schrödinger model that describes how the electron is behaving within its orbital. So the first quantum number that we're going to learn about is called n. That's called the principal quantum number, and it's a positive integer. 1, 2, 3, 4, 5, 6, or 7. We don't find in naturally occurring atoms n bigger than 7. N was also found in the Bohr model of the atom. L is called the angular momentum quantum number, and it is an integer that runs from 0 up to n equals 1. So if n, say for example, equals 5, then possible values for L would be 0, 1, 2, 3, or 4. Okay. ML is referred to as the magnetic quantum number, and it can have both positive and negative values that run from -1 up to +1. So for example, or minus L, sorry, up to plus L. If L equals 4, possible values for ML would be -4, -3, -2, -1, 0, 1, 2, 3, or 4. Okay, so minus L to plus L. MS, we're going to talk about that later. But the location of the electron, the atomic orbital of the electron, requires these 3 quantum numbers to be input into the Schrödinger equation in order to calculate it. So what do they represent? So the principal quantum number, n, describes the size of the orbital. That is the general distance of the electron from the nucleus. So the larger the value of n, the more likely the electron will be found at a greater distance from the nucleus. This is typically referred to as being the energy level of the electron or the shell of the electron. And n for the naturally occurring elements is a positive integer somewhere between 1 and 7. The angular momentum quantum number describes the shape of the orbital. Sometimes this is referred to as the subshell type. L can take on values in the known atoms between 0 and 4. 0 and 3. Sorry, a bit sleepy. So L equals 0 is also known as an S subshell. L equals 1 is also known as a P subshell. L equals 2 is also known as a D subshell. And L equals 3 is also known as an F subshell. Now, you might have heard these subshell names in previous chemistry classes. Our third quantum number that describes an orbital is the magnetic quantum number ML, and that describes the orientation of the orbital with respect to the x, y, and z axes. ML takes integer values that range from -L all the way up to positive L in increments of 1. So for example, for an S subshell, that is an electron that has L equals 0, there's only one possible value of ML, that would be 0. For a P subshell, where L equals 1, ML can be equal to -1, 0, or +1. For a D subshell, where L equals 2, possible values for ml would be -2, -1, 0, 1, or 2. For an F subshell, where L equals 3, possible values for ml are going to be -3, -2, -1, 0, 1, 2, and 3. So there is only one possibility for the orientation of an S subshell. There are 3 possibilities for a P subshell, 5 for a D, and 7 for an F. Now, what about that 4th quantum number, ms? Where did that one come from? Well, if you take a stream of hydrogen atoms, which each have 1 electron, and you pass it through a magnetic field, exactly half of your atoms will be attracted towards the north pole of that magnetic field, and exactly half of them would be attracted towards the south pole of that magnetic field. That is, the atoms behave as though magnetically the direction or orientation of their magnetic pole is quantized, with half of them having their north pole directed up and half of them having their north pole directed down. That's why 50% of them go in each direction. That is, magnetically, they seem to be quantized. So why would a charged particle have a magnetic field associated with it? Well, that would be because the charged particle was spinning. So when charged particles spin, they create a magnetic field. So this is indicating that half of our electrons are spinning in one direction and half of them are spinning in the complete opposite direction. The spin of the electrons is quantized. Half of them are spinning one way, half are spinning the other. So the electrons behave as though they are spinning, and that's why they have a magnetic field associated with them. The electron spin is quantized, and there's only one of 2 possible values. They're either spinning up, so that their north pole, or they're either spinning such that their north pole is oriented upwards, or they're either spinning such that their north pole is oriented downwards. So we're going to describe the electron spin by the spin quantum number, ms, and that can have a value of either +0.5 or -0.5. So now our set of quantum numbers that we need for the Schrödinger equation is complete. We have n, the principal quantum number. We have L, the angular momentum quantum number. We have ml, the magnetic quantum number. And then finally we have ms, the spin quantum number. And if you put those 4 quantum numbers into the Schrödinger equation, it will give you a description of where the electron is in terms of its orbital and also the energy of that electron. So it's like a souped up version of the Bohr model. Now the Bohr model is obviously much easier to use because we only have the one quantum number, n, but the Bohr model only works for when we only have one electron. So the Schrödinger equation is an improvement because it works for any atom. So we now have the basic fundamentals of modern quantum mechanics. People now are just kind of like working out what the consequences of this are. And one of the things that got worked out by a guy called Wolfgang Pauli is that it's not possible to have 2 electrons in the same atom with the same set of all 4 quantum numbers. So what practically this means for us is if an electron, or if 2 electrons have N, L, and Ml the same, then their spins must be different. So when they have M, L, and Ml the same, that means they're in the same orbital. So they must have different spins if electrons are in the same orbital. Now, as there's only 2 possible values for ms, plus a half and negative a half, that really means that if you put the maximum number of electrons that you can put in an orbital is 2, and if you do put 2 electrons in the same orbital, then they have to have opposite spins, right? So you can put a maximum of 2 electrons in an orbital, but they have to have different spins. Okay, so that's a cool result. Okay, so let's have a look at some of these radial probability distributions to see what they look like. So these are all the radial probability distributions for 3 S subshells. So for the first 3 S subshells, so this is for n equals 1, n equals 2, and n equals 3. And as they are S subshells, they all have L equals 0. So rather than writing n equals 1, L equals 0, we can abbreviate that as 1S. The S tells us the subshell, and the 1 tells us the principal quantum number. Okay, so what you see is we get a curve for the 1S with a peak exactly at the position predicted for Bohr by Bohr as being the radius of the n equals 1 level in the hydrogen atom. Now, when we move on to n equals 2, L equals 0, or the 2s subshell, our major peak moves out to larger radius, and you see that we have a node here, and then we have a smaller peak where that curve penetrates in closer to the nucleus. When we move out to the 3s, again, the major peak moves out to a greater distance from the nucleus. We have 2 little peaks where we penetrate very close to the nucleus, and we now have 2 nodes for the n equals 3, L equals 0 subshell. So as we increase the principal quantum number, we increase the number of nodes, and we also increase the positions where the electron penetrates close to the nucleus. Most commonly, subshells are represented by what we call probability distribution diagrams. So these are 3-dimensional representations that enclose a particular probability in space. So normally these are drawn as 90% probability diagrams. So for the 1s, because it's an S subshell, it looks like a sphere, and there's a 90% probability that the electron will be found somewhere on the surface of that sphere. For the 2s, again, because it's an S subshell, it's spherical. It's bigger now because we're out to n equals 2. And they've used a change in color in the cross-section to indicate that there is 1 node and also like 1 region where the electron penetrates closer to the nucleus. For the 3s, again, because it's an S subshell, the diagram is spherical. It's even bigger than the 2s, and you can see now there are 2 changes in color because they are trying to indicate that there are 2 nodes here. So every time there's a change in color, that's where there is a node. We can also draw similar radial probability distributions for P subshells, that is subshells that have L equals 1, and we see a similar pattern. So we can't have L equals 1 until N equals 2, but the 2P subshell kind of looks like a similar kind of shape as for the 2S. We have one peak and we have no nodes and we don't have any penetration of the orbital. When we go out to N equals 3, L equals 1, that gives us the 3P subshell. The principal peak is moved further away from the nucleus. We have one node and we have a little peak where this is penetrating closer to the nucleus. And again, when we go out to N equals 4, L equals 1, that gives us the 4P. We have the major peak here, even further out than from the what we see for the 3P. And we have two nodes and we have two regions where the electron penetrates closer to the nucleus. So the same trend as what we saw for the S subshells. As we move out to higher principal quantum number, we get more nodes and we get more regions where the electron penetrates close to the nucleus. So looking at the 90% probability surfaces for the P subshells, what we find is that P subshells are represented or are composed of two lobes that are located each side of the nucleus, and these kind of look like bun-shaped lobes, although typically people will draw them as teardrop-shaped lobes. There's always going to be three orientations for these, because if L equals 1, then ML, which represents the orientation, can be -1, 0, and +1. So we'll see a set of three P orbitals making up a P subshell with three different orientations, one directed along the x-axis, one directed along the y-axis, and one directed along the z-axis. An S subshell has L equals 0, so there is only one possible value for the orientation of an S subshell. So there's only one orbital in an S subshell, and that S subshell is spherical shaped. As I just mentioned, a P subshell has L equals 1, so ML can have three values. That is, there are three possible orientations for a P orbital that make up a P subshell. So we have a set of three P orbitals in this case. Now, for an electron that's in a D subshell, L equals 2, and we can see that there are 5 possible orientations. The typical shape of a D orbital has 4 lobes in this kind of clover leaf arrangement, but we do notice one exception where it has these sort of like, it looks almost like a P orbital, and then there's an additional torus around the middle, sort of bisecting those two lobes. So that one's kind of a little different. So yeah, we get the 5 orbitals with their 5 different orientations, and in one case we actually get different shapes. Put that all together and that's a D subshell. Now an F subshell is going to be quite complicated. Orbitals that are in an F subshell have L equals 3, and then that gives us 7 values for ML, and every time we change the orientation, we also change the shape slightly, and so you get a really complicated set of orbitals composing an F subshell. Now, what you really want to be mindful of is just being able to distinguish from diagrams whether something is an S, P, D, or F. And I think most of us are going to be able to do that because F just goes crazy. And if you were to see diagrams of these things, I think you would be able to tell whether it was an S, P, D, or F subshell. Okay, so that concludes section 6.3, which gets us all the way through the development of the modern quantum theory.